Okay, now we are into the another part of electrostatics, that is Gauss theorem. Gauss theorem. Okay. Usually, in our general language, they will be calling it as Gauss theorem. Gauss theorem. So we can call whatever name if you want, you can use, but actually it should be pronounced as Gauss. Gauss, not Ghouse. It is Gauss. Okay, Gauss law. Okay, so it will be Gauss law like this, or Gauss theorem. So in this is an important concept, and this Gauss law is also considered as the fundamental law in physics, which helps us to calculate the electric intensity of certain surfaces, and this will be considered as an easiest method or the fastest method for calculating the electric flux through a surface, because when we apply this method we can solve the problems with what you call it as the simple simplifications, not having much simplifications. So that's why we prefer this theory. Here, when you are going to calculate electric intensity due to a charged conductor, electric intensity due to a charged conductor. Charged conductor may be, this charged conductor may be of what you call it as uniformly charged sphere, or it is a line of charge, or electric dipole. So electric intensity due to charged conductor. The conductor may be of uniformly charged sphere or line of charge, electric dipole. We will be calculating this by using Coulomb's law. So far we did this method by using Coulomb's law. And electric intensity can also be determined, the electric intensity due to a charged conductor. Now we have found this by, up to now we just went with the Coulomb's law. And this electric intensity due to charged conductor can also be done by, this is Gauss law, except electric dipole. This is to be noticed. Except electric dipole, we can apply the law for finding the electric intensity due to a charged conductor. Why it is not applicable for electric dipole means there will be no symmetry. Symmetry will not be there. And so because symmetry will not be there, whenever the symmetry is not there, no other way we have to go with. If the symmetry is not there, we have to move with the Coulomb's law only. If symmetry is there, happily you can use this Gauss law and you can calculate the electric field intensity. Okay. Now, already I told you that why we prefer, even though for some type of what do you call it as the charged conductors, we cannot go with this Gauss law. Even though we cannot go with the Gauss law, we prefer using Gauss law, because the reason is this is the fastest method, and if the body is having symmetry, like a sphere, a cylinder, a plane, If they have the symmetry, happily you can go with this Gauss law instead of going with the Coulomb's law, because this, while making the calculations, it is not necessary to go with 1 by 4 pi epsilon naught, making all the calculations, not necessary. Simply charge divided with a small number, that's enough, we can complete the problem. So that's why we prefer this, what you call it as Gauss law. Okay, so now if the charged conductor is not uniform, or if it is not having what you call it as spherical symmetry, or if it is not having cylindrical symmetry, if it is not having planar symmetry, we have to go with Coulomb's law. Okay, so keeping this in mind, we apply this Gauss law. Okay, now before going into the Gauss theorem or the Gauss law, we need to understand certain things here, like vector nature of area. Vector nature of area. Already in your 11th class, in certain discussions, we came to know that the area is also a vector quantity. And how this vector will be there? Suppose if an area is there, suppose a surface is there, and the area. So up to certain level of classes, we understood that this is a scalar quantity, and from 11th class onwards, we started understanding it as a vector quantity, and that vector means it will have a direction. How this vector will be there means it is perpendicular to the surface or normal to the surface. So like this, your area vector will be there. So this is the vector nature of area. What we have to understand and keep in mind, this helps us now we go with this for finding out the electric flux or electric intensity and applying this Gauss theorem or the Gauss law. And next is electric flux. After understanding the vector nature of area, you have to understand about this electric flux. Electric flux. So here, what is this electric flux? What is the use with the electric flux? That means electric field can be quantitatively understood. Electric field can be quantitatively understood if you using this electric flux. Electric flux is denoted by phi. So electric flux is denoted by phi, and how to understand this electric flux means electric flux is a number. It's a number. So what is this number means? It is the number of field lines. So it is, first of all, it is a number, and it is the number of field lines, and the number of field lines which are coming out from the surface, perpendicular to the surface, will be, and these field lines are normal to the surface. So that we will be calling as the electric flux. And this electric flux is a scalar quantity. It's a scalar quantity. And let us see how to find out this electric flux. So this electric flux, this electric flux is what you call it as, depends upon electric field is generated by the electric flux, and we know that electric field lines start from the positive and end at the negative, and number of field lines depends upon the size or quantity of the charge. More is the quantity, the intensity of the field lines will be more, as you already learned it in our earlier classes. Okay, now let us know how to find out this electric flux. Suppose if a surface is there, and this is the electric field E, and if a normal is drawn from the surface, this is your normal drawn to the surface. Now what is the electric flux in this case means phi is equal to EA. Like this will be going. And we know that area is a vector and this is a vector, a dot product which always yields a scalar quantity. So like that it became what you call it as a scalar quantity. Now phi is equal to E by A, and let us, by using this we can give the units for the phi, electric flux. How to give the units for this? Already you know F is equal to QE, E is equal to F by Q, force will be in Newton, Q will be in Coulomb. So Newton per Coulomb, by this we can understand E is Newton per Coulomb. If you forget, you can extract the unit like that. It is Newton per Coulomb meter square. Area is in meter square. So the unit is Newton meter square per Coulomb. So this is the unit for the electric flux. So phi is equal to EA. So all the times we cannot see the electric field is always in the direction of the normal. That means in the direction of what you call it as the area vector. So there might be, we cannot see every time parallel to this electric field parallel to the normal. It may be having some angle other than this. Suppose if your surface is like this, and if your normal is like this, and if your electric field is in this direction, that means if theta is the angle between, E and normal, then phi is equal to EA cos theta. Phi is equal to EA cos theta. So like this you can calculate phi if electric field is making some angle with the normal. If electric field is making some angle with the normal, you can use this formula for going with this for finding phi. Phi is equal to EA cos phi. So now if we understood like this, supposing this surface, and if this is the normal, and if electric field is in the parallel to it, if E parallel to the normal, that means theta is equal to 0, then phi is equal to EA cos theta, that means cos 0. Cos 0 is 1, so phi is equal to EA. If sometimes if this is the surface and if this is the normal and if electric field is in this direction, now E is perpendicular to N, that means theta is equal to 90 degrees, phi is equal to EA cos 90. Cos 90 is 0, so this becomes 0. So phi is equal to 0. So this is how we go with for finding the phi. Okay. Now pause the video and take the screenshot. Okay. Now let us talk about the surface, which is a closed surface. If you look into any closed surface like a sphere, we will understand one thing from this closed surface. Suppose if we just consider this as the space, and if this as the space, and just look at the surface here, this surface is separating the outer region from the inside region, outside region and inside region. That means the surface is, what about surface? Closed surface is separating outside region with inside region. And if one has to move from outside to inside or inside to outside, it is not possible without crossing the region. It means without crossing the surface, one cannot move without crossing the surface. So that is what we understood from this closed surface. Such type of closed surface, we will be calling it as the Gaussian surface. Such type of surface we will be calling as the Gaussian surface. We find some much use with it, with such type of Gaussian surface. So here, Gaussian surface, what is a Gaussian surface? A Gaussian surface is a closed surface which separates outer region from inner region. So one cannot move from one region to other region without crossing that surface. Such type of surface are called as the Gaussian surface. So here generally how this surface should be. So for this surface to be, it can be of any shape. First, it should be a closed surface. A Gaussian surface should be a closed surface, and it can be of any shape, and it will be more useful if it is what you call it as spherically symmetrical, or if it is cylindrically symmetrical, or if it is planar symmetrical. So how a Gaussian surface should be means it should be a closed surface. It can be of any shape, and it will be more useful. It can be of any shape, of course, but if it is of a type like spherically symmetrical or cylindrically symmetrical or planar symmetrical, it will be more useful to us. So this we will be calling this is about the closed surface. And regarding the electric flux of a closed surface, so here electric flux of a closed surface is the integral of the closed surface S, E dA. Okay, that means this dA represents the small region. So on the surface we are going to take a small region, and finding the electric flux from a small region. Similarly, so many small regions will be there around the surface. So because of that, we go for integration, and in this, when we are integrating, to make everything understand, or to make us understand, or to others understand that the surface, for a surface we are going to calculate this S we keep here, and to understand that it is a closed surface we keep a circle here. So the integral of closed surface S E dA. And suppose if this also can be represented in another manner, integral of closed surface S E n cap dA. In addition, we have added n cap here. This n cap is nothing but it is a unit vector perpendicular to the surface, or normal to the surface. So that we will be calling as so how to find out the electric flux for a closed surface. So this is the formula we use for the closed surface, for finding the electric flux for the closed surface. Integral of a surface which is closed, integral of closed surface E dA. Okay, so this is the formula what we use. Okay, now this is the concept, and before going into this theorem, we will be going with 2 or 3 problems, then we will go with this Gauss theorem. And now pause the video and take a screenshot. We will go with 2 problems, small problems.